So thank you very much for the introduction. Yes, I am Lang Hames. I'm a compiler engineer at Apple, and this is powering Xcode Previews with LLVM's Awk JIT. So this is Xcode, it's Apple's IDE, and Xcode Previews is a feature where if your application has some Swift UI code, like the Hello World UI that we've got on the left here, you can use the preview macro shown on the lower left hand to get a live preview of your UI. The idea being that as you edit your UI code, you get fast feedback on the changes that on what the changes to your code are doing to your actual running UI. And this is your running UI. We don't interpret or anything. We're running your program and reflecting the UI into Xcode's canvas. So you can interact with it and do anything else you can with your app because it is just your app. Now, when we introduced this feature, the way we made it work was to do a second build for this. You have your regular debug build, but then you had a separate previews build that had a layer of indirection added to enable fast function replacement. Now that worked well. It means that when you edit the code, we can quickly swap out functions to show you the new UI. But it did mean that we were building twice. So as of last year, we've replaced this with a scheme based on LLVM's JIT. In the new scheme, we're loading your object files from your regular debug build and using the LLVM JIT linker APIs to add the indirection we need for fast function updates. This is great. We get rid of the second build, but it means that LLVM's JIT needs to be able to load and run any application that we would have statically linked and run under the old model. So these programs can get large, thousands of files, hundreds of megabytes of code and data, hundreds of thousands of relocations. And it's common on macOS for programs to be split up into multiple frameworks and libraries, so the UI code might not all be in the main executable. These programs can also get weird, so mixed languages are very common here. You must have some Swift code to use Swift UI, but Objective-C is also very common, C and C++ also, and other languages are used too. And it's also fairly common for projects to include precompiled static archives that the project needs to be able to link against. We might build with multiple slices turned on, say ARM64 for Apple Silicon and x86-64 for Intel Macs, and we need to be able to pick the right slice. We might adopt non-trivial entitlements that change the behavior of the execution environment, like the macOS hardened runtime, which we'll talk about in a moment. We might adopt interesting linker options like -r, weak loading, and hidden linking, which I'll talk about later, and interesting assembly options. We do see some handwritten and machine-generated assembly, which differs from the assembly that might be generated by Clang. So we need to be able to handle all of that in order to run this previews feature. The setup of the JIT that we use to enable this looks like this. We always take advantage of Awk's ability to run in cross-process mode. So you have a controller process that contains the previews JIT and a separate executing process where the JITted user application will run. And this allows us to avoid polluting the executing process with the details of the JIT and the libraries that it depends on. As I mentioned, we're only loading object files here, so there's no laziness in previews. We're taking the object files from the built products directory of your debug build. We install what we call an override plugin into the JIT linker, which allows us to modify the object files as they flow through the JIT to add the indirection needed for fast function updates. We use a custom memory manager to transfer the code and data from the controlling process to the executing one. And in the executing process, we use what I believe is a novel dynamic loader integration in order to present that JITted code as if it were precompiled. Finally, to deal with the scale of these applications, we always make use of Awk's ability to concurrently generate symbols. So we'll be linking multiple object files concurrently. And I'm going to step through each of these parts in a bit more detail. We'll start with the override plugin. This is fairly self-contained. We were able to do this because the JIT linker APIs are designed to give you a lot of flexibility with how you deal with the machine code flowing through the JIT. In particular, the JIT link APIs can rename and add code and data. So adding some indirection is easy. The first time we see a function, all we have to do is rename that function to make sure that the name doesn't clash with any other symbols in our program. And then we introduce a stub with the original name and point the stub pointer at the original implementation. So everybody who references the foo function is going to bind to the stub, and we can redirect that stub at runtime as we like. So if we want to replace this function buddy either at runtime or at process launch, We can load a second definition. That gets renamed to ensure that it doesn't clash, and we just update the function body stub. Now, it's out of scope for the previews JIT to decide when this is safe. We punt that to our clients, and they have a way to know whether they can replace a function on the fly while the program is still running, or whether they need to do a process restart. But this is very easy to express with the APIs that are already in tree and LLVM. The memory manager changes that we made for this project apply code signing to JITted code. Now, we're not doing this for security. We're working in an IDE here. The whole idea is to let you execute arbitrary code. But we sign code so that we don't affect the behavior of apps that adopt the macOS hardened runtime. So this is an entitlement that you can opt into that says, I do not want my process to be able to load unsigned code. So by default, it disables JITting, and it means that you can't load libraries that don't have a valid code signature. So this is great for preventing code injection attacks when you're deploying your app, but it poses a challenge here when we want to inject the entirety of the app. So rather than disabling this or working around it, we can make this work without reducing the security of the hardened runtime by introducing a custom entitlement called the previews signature type. Not a custom entitlement, a custom signature type that works with this entitlement. It is only applicable for programs that can have the debugger attached. So we're not weakening the security of the hardened runtime. You can't use this in arbitrary places. But what it means is that when we load code for the JITted preview, we're loading valid signed code, and the hardened runtime is happy. The interesting thing is that the JIT linker APIs are flexible enough to easily represent this. So our memory manager API allows us to split the linked code, which we send via shared memory. Linked data goes via shared memory from the linked code. To attach code signatures, we have to create files, because in macOS, signatures are attached to files. So every linked code section gets written to disk as a file, signed, and then mapped into the executing process at an assigned address. The code that's being loaded is signed, the hardened runtime is happy, and all of this works. This is very macOS specific, but I share the story here because if anybody's been interested in using the LLVM JIT but thought, I work in a constrained environment and I'm not sure that the JIT APIs could work here, you can often get the JIT to work just by customizing the memory management interface to deal with these kinds of issues. So the most interesting part of this project for me personally is the dynamic loader integration. And this came out of a question that seems like a corner case, which is what should DLSym of foo return if the symbol foo is in JITted code? Right, so for those who don't know, DLSym is an API that lets you look up C symbols by name. If you call DLSym and give it the string main, you expect it to give back a pointer to your main function. So the answer is that DLSym of foo should return the address of foo. That's what it would have returned if it was precompiled, and we don't want that behavior to change. The problem is that this call to DLSym might be in precompiled code itself, which is outside the JIT's control. DLSym on macOS is implemented in the system dynamic loader, so we need the dynamic loader's help with this. So the way that we approached this was to teach the system dynamic loader to treat JITted code as if it were precompiled. You can think of this as a pseudo-dynamic library, where the behavior of the dynamic library is provided by APIs and callbacks rather than by the dynamic loader reading a file in a known format on disk, like Marco or ELF. And where in this case, the callbacks will be implemented by our JIT compiler. The advantage of doing this is that POSIX APIs like DLSym and DLOpen are very naturally supported, but much more interestingly, in this world, precompiled code can bind against JITted code, which means that you can selectively JIT individual dynamic libraries. To see the advantage of this for the previews use case, consider an application like this with multiple libraries, where we want to edit UI code that's down in the libui library at the bottom of the tree here. In the old world, where precompiled code can't see JITted code, we would have to JIT every library back to the root, not because we actually want to JIT them, just because that's the only way for them to bind to symbols in the levels below. In this world, where JITted code is visible to precompiled code, we can JIT only the parts that we want. And the performance opportunity is that you JIT the parts that are changing, precompile the rest, and that gets you the best of both worlds. We're never going to beat the system dynamic loader at loading unchanging pre-linked code, but we can just reuse it and focus the attention of the JIT on the code that's changing. And if you're wondering how you could actually statically link that libbar library when you might not have a libmyui on disk, that's exactly the problem that the LLVM text API libraries solve. So they allow you to take just a symbol table, essentially, for a dynamic library and use that to link against without having to have a full dynamic library compiled. If you're interested in learning more about text API, you can check out the talk Using Tappy to Understand APIs and Speed Up Builds, which I've linked at the bottom of the slide. So the reason this works is that there aren't that many things you can do with a dynamic library. You can create a new library at a path. You can open it once it's there, which is going to run the initializers. You can look up symbols and addresses within it. You can close a library, which will run the deinitializers. And finally, you can delete a library, at which point it's no longer openable. So what we're going to do is turn each of those operations into an API or callback. So create becomes register. It takes a set of callbacks, an address range, and a loadable at path predicate that you can think of as introducing a virtual file system to the system dynamic loader. Whenever the system dynamic loader comes up with a path that it might want to open, if there's no file on disk at that path, it can ask the registered pseudo dilibs, are you loadable at this path? If one of them says yes, the dynamic loader can say, right, run your initializers, you're being opened. If the dynamic loader needs to look up any symbols within the pseudo-dynamic library, it can call the lookup callback, which will be forwarded to awk core lookup in our implementation, which we'll see in a moment. But the interesting upshot of this is that symbols in a pseudo-dynamic library do not need to exist in any way in the executing process until somebody looks them up. So the pseudo-dynamic libraries can be populated lazily. And we don't even have to compile something when you reference it. If you reference a function, which means you need an address for it, you can use awk's lazy reexports facility to quickly generate a stub that will arrange for the function body to be called at runtime if anybody actually executes it. So while we haven't done any laziness in this project, I've built a proof of concept out of tree where you can have something that behaves like a dynamic library, but the dynamic library is backed by totally uncompiled source code that's being compiled lazily as you use the dynamic library. So the last two operations are deinitialize, which runs the deinitializers, and deregister, which is the moral equivalent of a delete, means that you can no longer open the pseudo dilib. The implementation of these things in the awk runtime was made simpler by the fact that we already have emulation of these operations in the JIT runtime. So we already had an emulated DLOpen and DLSym, all the other operations. So for this project, we just had to add the glue code to align the interfaces, modify the internals to add some caching for performance, and adapt to DYLD's locking scheme. And we added auto registration and deregistration so that when you create JIT dilibs in the controlling process, a corresponding pseudo dilib immediately becomes openable in the executing process. So I wanted to run through an example of what it looks like for precompiled code to bind against JITted code in this world. So we've got our executing process running the system dynamic loader and containing the awk runtime, and separately our controller process has our previews JIT in it. And let's say we're in the middle of opening a precompiled library called libfoo, which contains an external reference to a symbol bar that we need to bind up. Bar is going to be defined in a pseudo dilib called libbar, but nobody has looked it up yet, so it has no address in this process. The definition of bar resides in an object file in the built products directory. It's been registered with the previews JIT, but no other work has been done for it yet. So what's going to happen is the system dynamic library is going to come across a reference to bar, and it's going to say, okay, I need to find the address of this symbol. It's going to call the lookup callback on the pseudo dilib, which will be implemented by the JIT runtime. The JIT runtime will call across to the previews JIT and say, I need the address of this symbol. Symbol lookup, as it always does in the awk JIT, is going to trigger materialization, so we're going to link that bar definition into our executing process. At which point the JIT knows its address and can return it to the awk runtime, which can return it to the dynamic loader, which can bind up the address. And we can now complete the open of our precompiled code, and our precompiled code is bound against this JITted definition. The practical impact and challenges of this, as I said, you can get the best of both worlds. You can JIT the changing code and statically link the rest. This is a substantial performance win on previews that are broken up into multiple libraries, because we can focus the attention of the JIT on the code that you're actually editing. It might seem like this might introduce a lot of inter-process communication, but that address caching minimizes the IPC. And in fact, we cache on whole object file boundaries. So you only need one round of IPC per object file that you link in, which is fine. Now this works, but we are adding inter-process communication in the middle of a library load, which is a really fundamental operation. And in fact, it's even worse than I've made it sound, because linking in that bar definition might require you to resolve external symbols that force you to call back into the executing process and poke at DYLD data structures on another thread while you're still in the middle of the library operation holding a lock. Now, we have made all of this work, but I consider it a bit brittle. I think we can improve this situation if we were to teach awk to use its own version of DYLD's bind operations. We could say that the JIT binds up the symbols that it knows about and returns bind operations for the external symbols that it doesn't. Those bind operations could always be run on the thread that is doing the DL open, and that would mean that as long as the system dynamic loader is using a simple recursive lock, this should be safe. So we hope to implement this in the future. So those were the changes to the execution environment. As for performance, the easy stuff, you turn on concurrency, right? This is easy only because we've been working on concurrency support since 2018. Nonetheless, with the scale of the code we're throwing at this, we did find and fix some race conditions, especially in Marco platform. We also had to introduce a custom dispatcher for this. So I hadn't mentioned them before, but when the JIT discovers that it needs to do some work, it doesn't just run it on the current thread, it'll hand that work to the awk dispatcher, which is a class that you can customize. In this project, we introduced one that has a fixed number of linking threads, but an unbound number of what we call request handler threads. And that's because requests between awk and the awk runtime are still, many of them are phrased as blocking operations. So you could starve a fixed size thread pool. We don't like this. We consider that a bug, and we consider the dynamic thread pool task dispatcher a hack. But what it is at this point is a battle-tested hack. So if you're looking to do large-scale concurrency with the awk JIT, and you're looking for something that has been tested, this is what we're living on. We're working on replacing all of those blocking operations with asynchronous operations. That would allow us to remove this restriction, and you'd be able to run on any thread pool that you like. We also had to make improvements to a lot of utility functions for this project, so I'll let one example stand in for many. The link graph split block operation breaks up content in the linker. For instance, the C string sections or the compact unwind records. This was ON squared for repeated applications. That had never showed up as a problem before, but with the scale of the code that we're throwing at it here, suddenly it was taking a long time. So we've added a cache, we've made this nlog n, now it's no longer a problem. And lots of other functions within LLVM's JIT have gotten the same treatment. The biggest changes for performance were within a data structure called the waiting on graph. So this is the data structure that allows concurrency in awk. It ensures lookup safety by tracking which symbols each symbol in the JIT is currently waiting on, so that they, what you're trying to prove is when somebody asks for the address of a symbol, are all of the transitively reachable symbols emitted, in which case I can use that symbol safely. So this is the data structure that tracks that. It was an arbitrary graph, and we were able to make it bipartite in this project by merging two of the old APIs in the LLVM JIT, add dependencies and emit. So you used to say, when you were materializing symbols in LLVM's JIT, I've discovered these symbols and these are their dependencies, and then separately, okay, I've written these symbols to memory, now they're usable. If you merge the two of these, you only tell the JIT about dependencies for symbols as you emit them. And you can partition that graph and say that you have a set of emitted nodes that is waiting on a set of unemitted nodes. That bipartite graph just ends up being easier to deal with in practice than the old arbitrary graph. And you can apply the same logic to pre-process the argument to the emit function that describes the dependencies of the symbols within your materialization unit. Getting into specific terminology here, but when you're materializing a set of symbols, you pass in a graph that say these are the dependencies. You can turn that into a bipartite graph using the same algorithm. You can do that pre-processing outside the JIT's global lock. So we can parallelize some of the work here as well. We also started applying coalescing to these nodes. So nodes within this graph that have identical dependencies are now merged into one larger node. And this is really helpful in practice because we see for large programs that lots of symbols end up piled up using a few common APIs that we're still trying to push through the JIT. So by coalescing these nodes, we massively shrink the graph. The waiting on graph has been lifted into its own type. It used to be embedded within the JIT dilibs. So the great news is that it is finally unit and performance testable, which it was not before. And as a little bit of extra polish, the node labels used to be reference counted types, but we were able to show that anything that was in this graph had corresponding references in the symbol tables elsewhere, so those reference counts were never going to drop to 0 and they were redundant work. So we were able to adopt the new non-owning symbol string pointer type as our label for the nodes in this graph, and that eliminated that reference counting as well. Taken together, all of these improvements were good for performance improvement on the order of 100x to 10,000x on some of our pathological cases. So in terms of results, I only have rough numbers. These are the numbers from the previews team for last week. This is not just the JIT load time. There's a little bit of preview-specific administration in there as well, so the JIT is slightly faster than these numbers would suggest. About 87% of the previews that we're running run in under 300 milliseconds. A further 10 and a bit % run in under 1 second. About 1.5% run in under 2 seconds, and the remaining 0.7% run in over 2 seconds. So we're happy with this as an initial result, but we have to be careful about interpreting these numbers because there's a couple of biases that apply here. The first one is that anybody who starts a new project and is playing around with this is going to fall straight into that 300 millisecond bucket, and that's going to inflate that one. And at the same time, for projects that do have pathological performance and see really slow previews, they're going to stop using the feature, and that's going to artificially shrink the longest category. We think that the performance so far is reasonable, but we know that there are pathological cases remaining, and performance work on this is going to continue, and I think we can make it faster. So finally, I wanted to talk about all the weird cases that you need to deal with to make this project work. The first problem I'll call naming archives.o. So the awk APIs are very strict. If you say you want to add an object file, we expect you to add an object file. If you say you want to add an archive, we expect you to give us an archive. The system linker on Darwin, by contrast, is very chill. It really just wants you to succeed. So file extensions don't matter, and as long as a file path resolves to something linkable, whether it's an object file or an archive or a universal binary, the system loader will link it. System linker will link it. So to match this, we've added the convenience function called awk load linkable file that takes a path, a triple, and a load archives option for whether you want to be able to load archives or not. And this will handle object files, archives, universal objects, universal archives, non-universal archives of universal objects, anything really that you want to be able to link. So this is now supported. LD-R. So LD-R is a linker feature that merges relocatable object files. And the interesting thing is that LD-R object files might contain duplicate symbol names, which object files coming out of a regular compiler never will. So for example, you can take two C files that have a static variable of the same name, run them through the compiler, LD-R together the resulting object files, and you'll get one object file with two symbols of the same name. And very few projects do this deliberately, but the Swift package manager does it, and so transitively through that, everybody ends up doing it. And this is sort of a common pattern, right? Features that seem really obscure, even simple programs often depend on them somewhere transitively in their dependence chain. So in any case, we've removed all assumptions that locally scoped symbol names are unique, and this is now supported. ARM64 pointer authentication. So this is a feature on ARM64 that allows you to add some bits to the high bits of a pointer, and the hardware is able to trap if anybody forges a pointer. So it's a control flow integrity measure. So we're able to support this in JITted code now, and interestingly, we're able to do it without introducing a trivial oracle. So we don't just have a function that says sign this pointer for the JIT. What we do is we install a linker plugin, and every time we see an authentication edge in our object files, our plugin replaces that with a null putter and it creates some instructions in a signing function that's run as a static initializer. And in this signing function, we're writing a fixed address with the signing bits attached into a fixed location. So my claim, at least, is that we can't use this as a general oracle. I'm waiting for a security person to tell me I'm wrong. There are so many more things that we did for this project that I wish I had time to talk about. So compact unwind is now supported. C++ exceptions will work on Darwin ARM64. Subsections via symbols. If you want a handwrite assembly on Darwin and you really don't like this directive, you don't have to use it anymore. Weak loading and hidden linking are both working. The -all load and -obj modifiers to static archive linking are working. And we know how to synthesize Objective-C stubs that use the new obj message send stub synthesis syntax. So all of this will now work. In conclusion, Awk can JIT load programs that were intended to be statically linked. It can scale to non-trivial programs, and it can support unusual build configurations and execution environments. And with dynamic loader support, precompiled code can interact with JITted code as if the JITted code was precompiled. We expect many of the benefits from this project to flow onto other clients of the LLVM JIT. And we think that there are new developer workflow opportunities to be pursued here. In particular, could we use a JIT mode for our edit test cycle? That is, rather than building everything that has changed, which is the normal incremental build model, could we build only what you need? This would mean faster compiles, but it would also mean that you don't need to select your build and target options to avoid unnecessary compilation. If I'm working on a bug-in LLVM code gen for x86, I don't want, while I'm doing that edit test cycle, to be building the other backends. Of course, this isn't a replacement for incremental builds. When I want to validate my change, I do need to run the whole test suite. So I think in an ideal world, we would be able to mix incremental compiles and JIT builds, and ideally share the content between them. The content addressable storage that people are working on would be ideal for this. So as a straw man, if you're trying to think about what would something like this look like, what if we took the LTO approach and had compilers produce .o files that didn't actually have any compiled content in them? We use the text API system to generate an interface, and we store the compile command, feed that through the build system, and then at the other end, run LLVM's JIT to execute the code. And there's all sorts of interesting extensions that we could think about for this idea: per function requests to the front end, changes to the build system and tooling. I don't have answers for how all this works. I have lots of questions. If some of you have thought about this and have ideas or opinions, I would love to hear them. If you haven't, this is your opportunity. So last up, in terms of future work, we need to move LLDB, this is immediate future work, move LLDB from MCJIT to Awk. That'd allow LLDB to benefit from this. The in-tree memory managers are very, very basic, and more people are living on them. I think there's a big opportunity to improve them here and benefit a lot of clients. The new Awk runtime is being brought up with all asynchronous operations and new features. The dynamic loader work that has been really interesting for us on Darwin hasn't been touched at all on Elf and Cough. And there are, if you can believe it, still a few open JIT bugs. So contributions are very welcome. If anybody's interested, reach out, GitHub issues, PRs, discourse discussions, or find me on the LLVM Discord. I would love to hear from you. All right, thank you very much.